So, good afternoon, all. So, this lecture which we are taking today is just the basics of ultrasound, including safety. See, you might find this lecture very boring. Boring in the sense we are going to talk about physics, but I'll make sure that you understand the importance of it. Having said that, what are we going to learn today? You're going to understand how an ultrasound image is actually generated. What are the various modalities of ultrasound which you see in your machine? You should understand by the end of the lecture what do you mean by artifacts and how you can avoid them. You have to also understand that what is the safety limits, because most of the scans what I'm talking about is going to be about pregnancy. So when we deal with early pregnancies, we know the sound waves, the heat energies can cause problems. So you should know what is the safe limit. So this is these questions are for all of you. If you don't know these, you have to learn it. See, before you learn how to drive a car, you should know what buttons are there in that machine, and you should understand what are the various equipments in your car. Because if there's a sudden breakdown, if you don't know, you cannot repair it. Same thing is with the ultrasound. You may be going to the ultrasound room, you may be doing your scans regularly, but many times we don't understand what actually ultrasound is, what is this real time, how this real time image is produced. And lastly, in today's lecture, you have to understand what is ALARA principle. ALARA is as low as reasonably achievable. Okay. Having said that, see, ultrasound is a sound wave. When I'm telling you that it's a sound wave, that means that it travels like a mechanical wave in a straight line. Please read this line. Longitudinal mechanical wave that travels in straight line. Every word in this sentence is important. Second point, it needs a media for transmission. That is why you use the gel which you put. If you don't put the gel, the sound wave will not transmit. If you have understood this, please understand that this sound wave, obviously, it will have a particular speed depending on the media, the temperature. The speed of the sound wave may vary. In an average biological tissue, the speed which is present is 1540 meter per second. I've put in red because this is one value. People will ask you when you talk about sound, and when they are asking you about physics or basics of ultrasound, they are going to ask you. Next, can a sound wave travel in a vacuum? No. That is the reason when you're doing ultrasound, you use gel in areas like, for example, if you put the probe in your umbilicus, what will happen? There is a vacuum, no? You will not get good images. There'll be a lot of shadowing. And to avoid that, what you can do? You just fill it with gel. That becomes a media which allow the sound wave to travel. How does this sound wave basically travel? Whenever any energy is traveling in space, what will happen? The particles which are present there in the space will be affected. And what will happen to that? Those particles will undergo some vibration. Okay. For example, the example which I take the best is, have you seen a sea wave? The sea wave, when it is traveling, and if you throw something like just a ball or some plastic bottle over the sea wave, what will happen to that? The bottle will move up and down. The bottle will move back and forth. That is how the sound wave travels in the media. These two movements will be seen. Because of these movements, what will happen? The place where the sound wave is traveling, at that particular point, there will be an area of compression. Then when the sound wave passes off, there will be an area of rarefaction. So by this, the sound wave travels in the media. I told you it's a mechanical longitudinal wave. And I told you this is very important. Why I told you that? For example, if your target is this ball and you want to hit this ball, and you know if you hit straight like this, you are going to achieve your target. But if your target is green and if you're hitting from here, do you feel you can achieve this target? No, na? So that is very important for you to understand how are you going to achieve your target. This ultrasound wave will only travel in straight line. Having said that, when, for example, during your ultrasound, you are measuring the femur length of the baby, okay? The femur length of the baby, for femur length, for you to measure the femur length, what you have to do? So these ultrasound wave, because they are traveling in straight line, what will happen? If this is your femur, for example, and the ultrasound wave comes and directly hit it at 90 degree, obviously all the waves will be reflected from this surface and you will get a beautiful image. But for example, now the femur is like this and your probe is here. Like this, the ultrasound waves are coming. What will happen? This part of the femur either will be, you will not be seeing it. Maybe you will misdiagnose that it is a small femur length. That is the importance of your probe positioning. Whatever is your organ of interest, you need to hit it at 90 degree so that maximum ultrasound waves reaches that object of interest. And if maximum waves reaches there, what is going to happen? You are going to get beautiful images. This is the importance of understanding the physics. Now, once you have understood this, one second, next slide. Yeah, this you have understood. Now, how we human understood that we can use the sound wave for producing such beautiful images. Now with 4D technology, I will be showing you one live 4D video which I have recorded for you all. We understood that this sound waves can be used to produce beautiful images on ultrasound machine, and we can use that. See, nothing we have invented. We have just discovered with what is already present. This technology, we human being understood basically from the nature itself. I'm showing you two photos over here. One is of dolphin, one is of bat. Both of these, everybody knows, no, bat cannot see, but have you ever thought how the bat flies easily? And we get scared seeing the bat, but bat will easily fly and bat doesn't come and hit us normally. How does that happen? Basically, they keep sending sound waves. With the sound waves, how they understand how far the object is and how big the object is, there are two more basic principles. First, the speed with which the sound reflects back. If the wall is very near and I throw a ball, the ball will come back to me very fast. With the speed will be very fast. Now the ball, I'm trying to throw a ball at a place which is very far. What will happen? The speed with which the ball will be reflected will be less. Same technology the bat uses. Second thing, the amount of reflection. If there's a bigger target, for example, if there's a mountain in front of me, whatever energy is going, everything will be sent back. And if there's a tree, what will happen? Some amount will be sent back to the person who is perceiving it, and rest will be scattered. Using this technology, the bat flies easily. We human beings started using this technology in World War II, and first this technology was used to understand the depth of the sea. Now, see, obviously, when you're transmitting some energy will be scattered, some will be lost in between, some will be reflected, because in the sea, if you're trying to measure the seabed, there will be fishes, there will be plants, there will be so many organisms. Every body, everything will keep reflecting. But the major reflection will come from where? From the seabed, which is your organ of interest, which is the depth you want to measure. So using this technology in ultrasound, we have started using and we have started measuring our organ of interest. Okay. Now, in medical field, mostly 1 to 20 megahertz is the normal wavelength which we use. Normal human ear can only hear 20 to 20 kilohertz. We all know that. That is why dogs and all, they can hear better and they can pick up infrasonic and other ultrasonic vibrations, which normal human cannot perceive. When we talk about the physics of ultrasound, what you have to understand, there are few basic things what you read about the wave. Just going back to our 12th class days, where we used to read period, wavelength, amplitude, frequency, velocity. Everything is not important in this. What is important in this is for you to decide which probe you are going to use best for your patient. Let us just know the definition of these things, and then practical utility of this we'll understand. When I talk about period, that means how much time one wave takes to travel. And what is the length of that is known as the wavelength. The maximum height which is achieved is known as the amplitude. Number of wave in 1 second is known as the frequency. And velocity is the speed. This is the simple definitions. Now, these are two pregnant women, both are 21 weeker. Do you feel that if you use the same probe, you will get better images in both the patient, or do you need to do some modification in your probe selection, in your ultrasound technique? See, basically, in ultrasound, the images which you see on the screen, and people who do it beautifully, and you say, oh my God, that's so beautiful. That is because they know their machine, they know their knobs, and they know how to play with their machine. Now, in a lady who is little obese, short height, the baby will be situated a little deeper. So you want your ultrasound to reach that baby, and so that you can get the images. But in a lady who is so thin, there is no depth. She's already very thin, and when she's very thin, the baby will also not be situated very deep. So here, this lady, you can produce beautiful images. Using this principle, you have to understand very important thing, that if you use a very high frequency probe means the number of wave which will be transmitted or released from the ultrasound probe will be more. If the frequency is high, the ultrasound images which will be produced will be of high resolution, but penetration will be less. Please mind it. This is very important. High resolution, high frequency. Means if you want to get beautiful image, please use high resolution probe. If in this lady who is so obese, if you use high frequency probe, your penetration will be very less, and you may not see your organ of interest. Whatever you want to see, you may not see at all. So you have to decide and choose which probe is best for your patient. In obese patient, you have to use low frequency. In thin patient, you have to use high frequency. Another point, when we speak about penetration, we understood that high frequency means less penetration. Can you see in this graph, in this box? At 10 megahertz frequency, the penetration is just 1 to 4 centimeter. At 7.5, it is 2 to 5 centimeter. At 5, it is 5 to 10 centimeter. And at 3.5, the penetration is up to 10 to 20 centimeter. This means if you're using your normal curvilinear abdominal probe, which you use, which has a frequency around 3.5 to 5, the penetration max you can get is 10 to 20 centimeter. But your TVS, that is transvaginal probe, intracavitary probe also you can call it, the frequency is around 7.5 to 10. What does that mean? Here you can get beautiful images. That is why for gynec scan, we prefer using a TVS, because we can produce beautiful images, we can classify better, but the penetration is less. So for example, if anybody has a fibroid which is of 18 centimeter, do you think a TVS probe will reach that? Will you get your outer boundary of the fibroid? Or if it's ovarian, if it is 20 centimeter or 14 centimeter, do you think that your TVS probe will give you the entire boundary, you will get the entire plane? No. Many a times, if the fibroids or whatever, any lesion of the pelvis, if it's too big, what has happened and what I have seen in practice also, patient scan was done, reported left ovary not seen, right ovary normal, uterus normal. And because the abdominal probe was not put for that patient, the cyst which was there in the abdomen, which was very huge, was missed. Whenever, this is one take home message for everybody, if you have planned, if the patient has come for a transvaginal scan only, then also just do a survey. Once put a TAS probe, scroll it up to down to see if there's something major you are going to miss. Okay, once you have done that, then you can go and do a TVS probe. This is very important, because this is a very common mistake which we do unknowingly, because we didn't put that transabdominal probe. So you have to know, see, nothing comes without any limitation. Everything has its own limitation. Everything has its own benefit. So you have to decide what is best for your patient. Now, once we have understood that, we have to understand one term known as PRF. This button, also known as scale, is present, and everybody plays with this button. Pulse repetition frequency means how many pulses are produced. I hope till now you have understood. If the number of pulses which is more, the images which is produced is beautiful, because that is directly proportional to the frequency. Okay. Now, how is this image produced? So basically what happens, from our ultrasound machine, electrical energy is transmitted through these wires into the probe. In these probe, there are few piezoelectric crystals. Piezoelectric crystals are some things like, I'll show you the images. They are crystal of quartz or all those things it is made up of. It has a technology, or it has a method. What it does, it basically converts this electrical energy to mechanical energy, that is sound energy. The sound energy will go and hit the target organ. The energy will be reflected back. It will be again picked up by this piezoelectric crystal. It will be converted to electric energy, which will go via these wires to the machine, where the CPU or the brain of the machine will interpret it as an image. And what do you see here as a media, which is helping this mechanical wave to enter the organ of interest? This is the gel which you use during your scans. So I told you this piezoelectric crystal is made of quartz, zirconium, and what they do, they transmit mechanical to electrical and electrical to mechanical energy. Now, how do we choose different probe, and why we choose these probes? See, if the crystals are very thin, I hope you will understand this. If the crystal is thin, no, in that, for example, if this is your probe and you place a very thin crystal over here like this. Now, if it is a thin crystal and you have chosen this probe, there is lot of space for this crystal to vibrate. So a thin crystal will vibrate very fast. But let's take this thick crystal now. The space is very less for this to vibrate. So a thin crystal can vibrate faster and produce high frequency. So in your TVS probes, the crystal which is there is very thin. But in your abdominal probe, there are thick crystals. They cannot vibrate that fast. So the frequency which is produced by this probe is low. So you get better penetration, but low resolution. So this is the basics behind why this TVS probe is producing more frequency, why this abdominal probe is producing low frequency. This depends on the size of the piezoelectric crystal. Now, that probe is not very simple. There are multiple layers. There is the lens, there is matching layer, grounding layer, piezoelectric crystals, and there is electrode. Now, this is the place where interaction happens, electric to mechanical, mechanical to electrical. Once the ultrasound wave is going, obviously, everything will not be reflected. Some things will be attenuated over there, some things will scatter here and there, and some of the energy will be transmitted. So, because of this, the amount which is reflected is going to decide how beautiful, how bright images you get. Let's now see. Reflection is basically responsible for image formation, because that is sound is coming back, that only is interpreted by the transducer. Transmission helps to see the deeper organ. For example, if you are looking at the liver, at the same time you want to see uterus or any pelvic organ, you just have to decrease the depth. The ultrasound wave will go deeper and will show you, because they are getting transmitted through the body. Next, attenuation. Obviously, some amount of energy will be lost because of attenuation of the energy. See, if you throw a ball at a particular speed, slowly, gradually, the ball will lose its speed and it will go somewhere and it will stop. So energy which you have transmitted will gradually wean off. Same thing happens in ultrasound also. Last is scattering. If, for example, if you are looking at the femur, now I told you if you're watching your femur and you put 90 degrees, you will get the entire femur. But if the femur is little like this, and the ultrasound wave which is coming like this hits the epiphysis. Epiphysis is a sharp point. Because of the sharp point, the ultrasound can get scattered here and there. This can lead to artifacts which you may encounter in your practice. Now coming to modes of ultrasound. Mode which you all use, and I know you all are very well aware of, is the A mode. It is the amplitude mode. And this mode you don't use mostly, because this is one mode which is now obsolete. Only clinical utility of this mode is to measure the depth of the globe. in the eyes. And here, the whatever ultrasound wave goes in the eyes, for example, you want to measure the depth, it will go, hit the wall, come back. It is shown in form of graphs, no real-time imaging. What we see in real-time imaging is the B mode or the brightness mode. And how does that happen? Let us understand that. See, till now you have understood that how energy is produced, how the energy is transmitted, what happens to the energy when the energy goes and hits your organ of interest. Now, how this beautiful image, those small dots which the ultrasound machine is sending, how it is producing that image of a face or abdomen or whatever you see. I told you, at every step, there'll be some reflection happening, and the speed with which the sound comes back will depend on the distance. So, ultrasound uses this formula of half the time of flight into velocity, and by this, it calculates the distance. And because everything is coming in one by one, back to back, it gives us an illusion of the shape what we are seeing. Now, the quality of the image in B mode basically depends on this shortcut form which I'm telling you. Define quality. D is for depth, E is for energy, F is for focus, I for frequency, imaging frequency, N for narrow or wide sector width, E is for your enhancement tool, that is tissue harmonic imaging in the SRIs. Q is for your quality control, that is the dynamic range. U is for your ultrasound frame rate. A is for your area of interest. L is for lateral adjustment that we do by time gain compensation. I for image persistence. T is for transmit power, and Y for your probe selection. Don't get confused what madam is trying to tell basically. These are the buttons in your ultrasound machine, which is going to define the quality of your ultrasound image. See, can you all see? All these buttons, lot of buttons are there, no? So these buttons, that short form was for this button. You may have to play with the gain, with the depth, with the focus, with the zoom, with the freeze, cine loop, probe selection, frequency, all this you have to choose. This is your time gain compensation, this one. What each button means and how to change it, I have a live video and live class for that. Maybe next class we can go for that, because this requires one. Knobology is a 1 hour lecture. So today we are just going to stick to basics of physics, and that is why we are focusing on that. But I want to show you that these buttons, these are your car ka equipments I told you, no? आपको पता होना है कि कौन सा ब्रेक का वायर है, कौन सा एक्सेलरेटर का वायर है, क्या पानी कम हो गया, so many things, no? Similarly, ये सब knobs से if you know how to play, you are going to be master in your field. Now, there is another mode. Two modes we have read, A mode, B mode. Now we are understanding what is M mode. M is motion mode. So which organ in our body is basically moving is the heart or the cardia. So this mode is used for measuring the heart rate, for the contractility of the heart, even in fetus, even in the adult. We measure TAPC, we measure MAPC, we measure the cardiac rate, we quantify or classify the types of arrhythmia. So this M mode is for motion. So this mode is used for that purpose. Now coming to 3D and 4D, how this 3D and 4D creates images. See, basically, in that ultrasound probe, no, there is a motor also. And when the piezoelectric crystal is sending the ultrasound wave, that motor keeps moving here and there. With that sweeping, what happened? Lot of slices of data is generated, and that slices of data is interpreted by CPU, and you get this beautiful 3D images. And this is used for fetal phase, uterine anomalies, follicular monitoring, antral follicle count. Now 3D and 4D is a basic requirement. It is the demand is increasing. The patient wants to see a 3D. What is 4D? How it is different from 3D? Have you ever thought of that? See, basically, 4D is a, oh, I'm sorry. So basically, 4D is 3D with time. When you have your 3D with time, it is known as the 4D imaging. Sorry, I don't know why this video is not playing over here. There was a video for you for 4D. Maybe from other slides I'll show you later after the end of the class. So basically in 4D, what we look at the baby's face, baby's behavior, baby's movement, everything you can see on 4D. I will show you. When I end the class, I will show you. This video is not playing. I'll play it separately for you. Now, what is duplex ultrasound? Have you ever thought of that? Or triplex? See, you read about so many mode. A mode, B mode, M mode. There is color Doppler, there is pulse wave Doppler, there are power Doppler. When you use multiple modes together, it becomes a duplex or a triplex ultrasound. Now you can see over here. We are using the grayscale B mode imaging. We have put on the color. You can see this red and blue. And we are quantifying it using pulse wave. So this is a triplex mode ultrasound. Okay. So when you are using all this, this is going to give you clarity regarding your images. Now, coming to one second. Just 1 second, I'll play that video for you. I'll stop the share. I'll play that video and then we can move forward.
Hello?
Just 1 second. I'm trying to play a video for them.
Okay, ma'am.
Yeah, I'm just trying to get that video. It's not playing, and that showing that 4D is very important for them to understand what is 4D. Any doubt if you have till now, you have to understand. See, this topic is very important. If you don't understand this, you will have problem in doing scans and playing with the knobology. The second lecture will not be of any use if you don't understand this. Anybody any doubt till now? Please post it now. We can keep on discussing by the time I show you the video. I don't know, somehow this video is not playing at all. It's okay. I can send the video later to you. So once you have understood all this, what we need to understand is about the artifacts. What do you mean by artifact? Artifact means the ultrasound image is not there for real. Many a times we get some things which are illusions. Those illusions you have to rule out in your scans before you actually interpret the report. See, mostly we see illusion when you have something which is very strong reflector. Like if you have a fibroid, what happens? No, by the boundary, the ultrasound waves will get reflected, and behind that, you will not see anything. So this is known as acoustic shadowing. What is the word? Acoustic shadowing. So there is shadow behind something when you have a strong reflector. What you can do? If you're hitting like this and behind this everything is black, just go and hit from the side. And if you remove that blackness just by changing the angle or the direction of the ultrasound beam, that means you are removing your acoustic shadowing. That was an artifact. And if it is actually something there, that will not go away. So this is one artifact. Many times we will see something known as posterior enhancement. See, like just see this. This is a simple cyst. And behind the cyst, in this area particularly, there is lot of echogenicity as compared to this area and this area. This happens whenever you have a cystic thing in front of your eyes. It can be bladder, it could be any ovarian cyst, anything. Because of that, the ultrasound wave is reflected from the inner margin of the cyst, and the other areas shows black. So this is also an artifact. Next is reverberation. This is very important when you're measuring amniotic fluid index. Or if you all have done amniocentesis or any invasive procedure, and if you have inserted the needle in the ultrasound multiple reflection like this you will see. And many times it becomes difficult for the person who is doing to actually know where is the needle position. For if you're doing abscess drainage, if you're doing amniocentesis, even if you're measuring amniotic fluid index, this reverberation, what happens basically? Between two strong reflectors, the ultrasound keeps moving up and down, up and down, up and down. Because of that, multiple images of that particular one structure is produced. So for this also, you just have to change the angle of insonation. See, why it is important. For example, if you start measuring amniotic fluid index, many people will just measure from here. Some may measure from here. They will think that this part they shouldn't include. So you have to take into account that you have to measure from here, not from here. Because if you miss this much part, you may label the patient by mistake as a oligohydramnios or something like that you may mention. So this has a very, clinically it is very important for you to understand that this is an artifact. If it is an artifact, means it is happening because of the sound waves which is traveling. It will go away if you change your angle of insonation. Next is side lobe artifact. This I told you just now, an example of epiphysis, no? So when you are seeing that, when you hit that one point, it will give you the, and you will feel, you will have a perception that there is something over here, but actually it is not there. It is due to side lobe artifacts. Amniotic band, so many times people do mention, and sometimes it's not a band. That also is due to artifacts mostly. So you have to change the angle, you have to decrease the gain, and you have to play with tissue harmonic imaging. What is that? We will discuss later. Now coming to safety, I told you, ultrasound is energy. When you're putting that energy on the baby, which is very small, you may, by your thermal energy, cause damage to the baby. So just to avoid that, you have to follow something known as the ALARA principle. You should keep the thermal index, the mechanical index to less than 1. And if you would have seen in your ultrasound machine, in the above, it will be written TI, MI. Every time it will keep changing, the machine. If you do the scan longer, it will increase. That is why you should do is for the shortest duration. This is known as low as reasonably achievable. Means the shortest duration which you can use is the best for your patient. Second, don't use higher end higher end ultrasounds like Dopplers, color Doppler, power Doppler. They can cause problem. Now, how long you can scan depends on this thermal and the mechanical index. For anybody whose TI is or MI is less than 0.7, you can keep on doing scan for whatever time. But as, just see here, as this TI MI is increasing, what is happening? The duration for which you can scan is going down. See here, when a TI is between 0.7 to 1, you can do scan for around 60 minutes. But if the TI or MI is more than 1, between 1.5, less than 30 minutes, you have to complete it. If it's more than that, then you have to decrease that further. In TI, on your machine, the two words will come. One is TIS, that is thermal index of soft tissue. And later, the word will be TIB, thermal index of bone. So before the bones are formed, you label it as TIS and then it is TIB. Now, when we talk about the ultrasound safety issue, as you choose more and more modality, for example, you chose triplex mode, means you did B mode, you did color, and you added your power Doppler. Sorry, pulse wave Doppler. You are increasing the heat energy which the sound will produce. You are increasing the power which the machine is using. You are increasing safety issues in the baby. So that is why in the first trimester, please, this is a very important take-home message. Next take-home message for everybody. Don't do pulse wave Doppler to measure the cardiac activity. Like for documentation, what we do? We use pulse wave, we measure the heart rate and when in the first trimester for dating. Don't do that. You can do that by M mode. It's pretty simple. Use M mode. Or you can just take a clip of that. If you don't know how to do M mode, what you can do? Focus on the baby, enlarge the image, press on your whichever button in your machine you have put as a video, cine loop, a clip. That machine will record a clip and you will see the heart beating with your eyes, and that clip you can save for your future use. That's all. And you can just say cardiac activity seen. That is all. So you are not caught in that medical legal thing that you have not documented the heart rate and you have not caused harm to the baby by using your power or pulse wave Doppler. So today's most important take-home messages are you have to understand what is ultrasound. Once you have understood what is your ultrasound, you have to understand why this TAS probe is used for abdominal scan, why this TVS probe is used. I'm asking these questions to you. If you have understood all this, our job for today is done. If you still have doubt, kindly ask me now itself. So first is how to choose a probe, depending on the patient, depending on your organ of interest. Then next is why you should understand now why this probe is better for this patient and this probe is better for that patient. Next, if you want to see something which is situated very deep, what you have to do? Choose a lower frequency probe. for better penetration. You should understand what are artifacts and how you can avoid them. You can avoid them by changing angle, decreasing gain, and playing with the harmonic imaging. Next, you have to follow the Alara principle and keep the TI and the MI as low as possible. So these are the basics of ultrasound physics. Next is you have to understand the knobology and transducer selection. Knobology and transducer selection, it's very long topic because the defined quality, what I told you, each and everything you have to understand how to change the depth, how to change the gain, how to adjust the TGC. And for that, I have videos for everything. I don't know why today 4D didn't play at all. If to any video, I don't know what happened. Suddenly the video stopped playing, but I'll show you one video if it's playing. Now, yeah, this is playing. See, before starting examination, I always tell my student, most important thing is how you do the entry, data entry. And this is how I'm entering my patient. You enter the ID, name, age, gender, and then you start the examination. Now, if you see this, I want everybody to be aware of what is written over here. This is written, I have chosen a gynec setting. I am using CA1-7 SD Pro, which is giving me penetration of 14 centimeter and the frequency is 32 Hertz. Can you all see that? Now, in every patient, I'll read and tell you so that you understand what is the meaning. Okay? What is all this? We will read it later. Everything we will read. Now, next I'll show you, okay, videos are playing. That particular video didn't play. So this is all the next class, what we are going to read. Now, this is the video of adjusting the gain for the patient. For example, you want to adjust the gain. Gain is what do you mean by gain? Brightness. Just watch this video. Just see, this is uterus, which is a very obese lady. You're not getting clear margins, but still see. Just increasing and decreasing the gain, how the clarity of this uterus is changing. I hope you all appreciated that. Now, next is the depth. This is the depth. 1 second, I'll show you. Yeah, let's look at this. This is frequency. See, this is what I'm playing with. This is the sector width. Sector width. We are increasing, we are decreasing. So these buttons, how to increase, how to decrease, everything we will discuss. It's a very pretty big talk. But you should understand that don't get like you should not be scared. Bapre, so many buttons, madam told. All these buttons you will learn, you will do it by yourself. That will come in next lecture when we go to the next lecture. So image optimization, the entire knobology is next lecture, which is upcoming for you all. In the physics, if you have any doubt, kindly ask now itself. Because if you are not clear with the physics, we cannot go and we cannot learn the other things in knobology. Before you reach that, you have to understand that. So lastly, I just want to tell you how to start the examination is next class. Now, somebody wants to ask anything, please, you can just unmute yourself. Somebody raised hand. You can write in the chat or you can unmute. I don't know. You can write in the chat box. I've opened it.
Yes, thank you. I don't know. Am I audible?
Yeah, you're audible very much.
Thank you. Thank you for the nice presentation and for the good topic. I have a number of few things to be clarified.
Yeah, sure.
One of it is about can all the ultrasound modes be applicable to one person? Maybe depending on the areas to do ultrasound.
I understood
And
your
then,
question. Your question number one is, let's go one by one. Your question one is, what ultrasound mode?
No, the
like,
question
should
is,
you? Okay.
what I was trying to say is that should one apply all the modes, like A mode, B mode, M mode, and the D3 to one person, or it depends on the area to be scanned?
A mode is obsolete.
Then question number, yeah.
Okay.
The next question is about artifacts. what could have been
About
the cause of these artifacts? The cause of artifacts.
Okay, next.
And then the last one is what happens when the TI is high or is more than 1 when you are scanning a mother, maybe in third trimester. Yes, a mother who is pregnant in third trimester.
Okay. So
And then the
question
last question is about the probe
I'll
choice.
forget the question. Okay, fourth question. Let me answer
Yeah,
3,
the last
then you
one is,
answer, but I'll also
the last one
forget.
is about, yeah, for sure. Yeah, the last one is about the choice of the probe. Like, for example, if the patient is fat, do we choose a probe which is of high resolution, or a probe which is of low resolution? Here I need some clarification. Thank you.
Let's go by fourth question that I remember now. So, see, the first thing is your resolution depends on the frequency. You can note it down. If you use high frequency probe, you will get better resolution. But the drawback is your depth, the depth to which you can see is hampered. See, simple, you cannot use one thing for every patient. You have to choose as per your patient. Like I told you, you have these of the two patients you are seeing. One is very thin, one is very, very obese. So in the obese lady, what you want? You want the waves at least to penetrate that fat layer and go to the baby. Otherwise, everything will be black, black. You will not see anything. So here you have to compromise on the resolution to get at least you see the head of the baby, you see the heartbeat of the baby, at least you see that. You might have seen in most of the reports, whenever there is obesity, people do write keep limited visibility or thick abdominal wall, all those comments we use in our reporting. So when you have obese lady, you don't have any option. You have to choose a probe where you want, where you get more penetration, though your resolution will go down. But in a lady who is very thin, you can produce beautiful image. Why will you use resolution probe? You use high frequency probe, you get beautiful image. Second question. Can you use one mode in all patients? Depending on the patient. First of all, A mode has only one use. You don't use it, you can forget it. Next is B mode, M mode, color Doppler, power Doppler, pulse wave. All these are modes. If you are doing biometry, like you're measuring the weight of the patient, what you need, what you want to measure the BPD, SC, ACFL, that's all. For that, you just need B mode. And for heart rate, maybe you will need to take the pulse wave Doppler. That's all. Now, but if that patient has not come for growth scan, she has come for Doppler scan. Now you have to do umbilical artery Doppler, uterine artery Doppler. You will choose you will choose that mode. How to choose the mode, I will teach you in the next class. But first of all, you should know these many modes are there and you have to choose as per your choice. In early pregnancy, you just need your B mode. B mode is basic that we do, that is the brightness mode for every patient, that is the grayscale imaging. Now, in that B mode scanning, if you want to measure the heartbeat, for example, it's 8 week, you cannot, I told you to avoid using pulse wave and power Doppler. What you should use? You should use your M mode. So here you needed 2 modes. Out of all those, you needed B and M. So it depends on your patient. It depends on your organ of interest. Next question is, what happens if the TI and the MI is high? If your thermal index and the mechanical index is high, the babies can have problem. Basically, in pregnancy, what happens? Like, for example, if you hit if you have a mirror in front of you and you put a lot of sound waves, heat energy, and keep it in the sun, the mirror can break, no? Similarly, this sound energy also produces heat. Whenever the heat is produced, it can cause mechanical effect. It's a mechanical wave. It will cause cavitational effect in the baby and baby can have problems. See, this I showed you. There'll be pressure will rise up in the baby. There'll be gas bubble formation. All that can happen. That is why there's a safety limit based on the TI and the MIs. If you're crossing that, please stop the scan. See, you will not cross that ever. Nowadays, the machines are so good, so beautiful. You will usually not cross that. But for example, if you're doing a level 2 scan, TIFA scan for a patient where the baby is not showing and you're doing for so long, you can do a better thing, no? You did for 5 minutes, stop the case, Tell the patient, please walk around, baby. I do TIFA. In the morning, I've done 5 TIFA before coming for the class. And 2 I have not completed. I have told them to wait. Why? Why? Because if the baby is, in particular, for me, the baby, both are prone. I'm not able to see the face and the heart. I have told them to wait, lie down, eat, walk. When the baby comes in position, I'll do it. Why I will keep the probe and keep transmitting energy when I know baby will take time to change the position. So we should avoid that. Next is, how do these artifacts happen? See, acoustic dropout like this one will happen when you have something which is not allowing the sound wave to travel. Like this is a fibroid. From the top surface of the fibroid, whatever sound waves are there, they get reflected. So below that, what you see will be black. But fibroid is like a circular thing, no, in your myometrium. Now from here you were doing, this all was black. You change and do from here, at least this area will be seen. You change and do from here, this area will be seen. So that can be, we can remove that. Next, artifacts which you can have is posterior enhancement. Posterior enhancement happens because of any cystic space in the body, ovarian cyst, umbilical cord cyst, whatever cyst. From the posterior wall of the cyst, the ultrasound wave will get reflected. Because what happened? No, if this is a cyst, sound waves is coming, it goes and hit, and from one point of that cyst, whichever is the strongest reflector of that cyst, from there it will be reflected. If you just change the angle, that reflection will go off. Artifacts are not problem. They can cause confusion. So anything which disappears, for example, you suspected short femur length. I'm using short femur, that is coming in my mind for now. You suspected short femur, change the direction, and once you change the direction, you got beautiful femur length. So that short femur was an artifact because your wave was not hitting the bone properly. You understand that? So these are the artifacts. This is why the artifacts happen. Reverberation happens when they are too strong reflector, like needle. If you have inserted a needle, the top and the bottom, both surface of the needle will reflect sound. And when there are too strong reflector present, the sound wave keep jumping in between like this. So this produces that artifact which you saw, this multiple needle ka image, this one. You saw because of that sound wave reverberation. Same thing, these line which you are seeing, this in amniotic fluid, this is nothing. There is nothing in the amniotic fluid. It's pretty clear. This is because the sound waves are getting reflected between the between the abdominal wall and the uterine layer. It keeps on reflecting like this. So that creates a reverberation. Any further question was there? If I'm not forgetting, I finished all the 4. Any further things I don't remember. Can re-ask. And how to choose a probe. You also asked how to do transducer selection and all. So basically, that I have kept in the can you see this? This I have put in the next lecture. How do we choose? We go to probe, we select this this is my machine, just touch. So we can go on selecting. You can just have to go and touch. So this is a intracavitary probe. This is your 4D probe. This is your linear probe, and this is your normal abdominal probe, that curvy linear probes. So you can choose these probes. So this is how you choose a probe. You are asking how to choose the probe. Which probe to use when? That is for the next class. Thank you, everyone. Any other question? We'll wait for another 1 or 2 minutes. If any question, you can ask. Otherwise, we can conclude. And the next class will be about probe selection. That will be pretty practical. This is boring. Physics is totally boring. I do agree. But at least now you understand why this probe is used, why this probe, how this ultrasound produces image on your screen. I'm feeling very bad because the 4D, I don't know why it is not playing at all. For sure, I'll send it to Kritika, and Kritika, you can transmit that video to everybody. I tried from
Sure,
various things,
ma'am.
but it's not playing. Only that video is not playing.